equal to the frequency multiplied by what we call Planck's constant. Okay, and that a photon with the frequency, it says here, over a certain threshold would have enough energy, it says, to eject a single electron, producing the photoelectric effect. It says here that photons have no mass. They actually said that in the video, that the photons they use the word massless in the video. They have no mass, but yet it has momentum, which is strange and crazy to me, because I'm going to come over here and say this is crazy because momentum, which is lowercase p, equals m times v. Do you recall that equation? How can you have momentum if you have no mass? And light, right here coming out of the projector screen, there it is. I have it in my hand. Ooh, I'm going to catch it. I can't put it on a scale. So since it doesn't have mass, how can it have momentum and literally push the electrons off of a surface? And that's what Einstein said it could do, which is a little strange for some people. It says here that it has momentum, and because it has momentum, then it can have energy. And since it has energy, these photons, then they're able to literally physically push electrons off of a surface. The photoelectric effect, it says here, is used in photoelectric cells, which convert a light energy into electrical energy. Boom. And there you have these people with these big panels on their roof, so that way they can convert the sunlight energy into electrical energy. Crazy how we can do this and how science is coming up with stuff like this. The photoelectric effect also has an application, for an example, on street lights. I don't know about you, but I passed up a couple of schools on my way in here, and these schools, they had people, crosswalkers. I guarantee you that the crosswalkers don't wake up and get there super early so they can walk and go turn on the light switch for those flashing lights. No, they have those little panels on top. And those panels are going to be automated to come on because they captured the energy from the sun previously, and they have energy already inside of them. The photoelectric effect has applications on street lights for automatic switch. They turn on automatically. They don't have to have somebody go turn them on for them. Traffic signals. And some of this was already said inside of our video. Burglar alarms, believe it or not. Burglar alarms. Elevators. Thank you, Einstein. Sometimes I try to take the stairs as much as I can. If you see me by the time I'm on the 3rd floor, I'm out of breath. But because of this, we're able to have elevators now. Solar panels. And these really cool things. Solar calculators. Right now it's not working. I'm letting the light shine on it right there in that little solar panel, and I can turn the on switch, and it'll work. Eventually I'll leave it over here, and not enough light, I'll put it back inside this little drawer, let it close and be in the dark, and guess what? It's going to turn itself off, right? It's those little solar panels on my calculators. All righty, so let's go ahead and summarize what we talked about the last time with Isaac Newton's thoughts and what we looked at these videos today. First thing is we have Young. His name is Thomas Young, and Thomas Young gets all of the credit because he came up with the double slit experiment showing that light behaves as a wave. And it can do this thing called interference, constructive and destructive interference. Now, Einstein gets this credit for the photoelectric effect and produce evidence that light acts as a particle. And these particles have momentum even though they're massless, and they can hit a hard surface and cause the electrons to come off, okay? In conclusion, it finally got to the point that some scientists believe the first one, some scientists believe the second one. Finally, we had to say, you know what? You can believe whatever, and you do you, and you do you. It's okay. But deep down inside, we're going to have to come to some type of an agreement. So the conclusion is that light acts like a dual nature. It acts like both a wave and a particle depending on the experiment that you are going to perform by the observer. Am I going to do the experiment where the double slit, or am I going to do the photoelectric effect? I can make light act like I want it to act, because light can act like both, and we call that dual nature, okay? The next portion over here that we're going to go over is called the laws of reflection. It says here that reflection is the change in direction of an electromagnetic wave at a surface. Which makes sense, right? You looked at a mirror this morning at this surface, it's a mirror, and the light changed from the mirror and then it went to your eyes and you were able to see your reflection. It says here, light traveling through a uniform substance, whether it's air, water, or a vacuum, always travels in a straight line. This is a guarantee. One more time, I cannot say this fact enough, that light travels in a straight line if it's traveling through a uniform substance, okay? I don't mean like it's going to hit a bumpy substance, a uniform substance. When light encounters a different substance, some of the light will be absorbed and the rest of it will be reflected. Or it's going to change directions. That's what reflection means. The amount of light absorbed and the amount of light reflected depends on the material it hits. Believe it or not, when you look at your mirror in the morning, not all of the image is coming back at you. Some of the light was absorbed in your mirror. So it depends on the material it hit, not the material, not all of the material will reflect out at 100%. Believe it or not, to get a perfect 100% mirror that's going to reflect all of the light and not absorb it or absorb some of it really doesn't exist. I don't know about you, but I try to make sure I'll clean off my mirror once in a while, not often, and it's not a super great image sometimes, especially if my mirror gets a little dusty or dirty, right? When you're ready, turn the page. Some of the problem is the actual texture. I don't know about you, but have you seen some really bad mirrors? Or have you ever gone to what they call a fun house, where those mirrors are a little different and you look at yourself and you look a little warped? Well, that's because of the material or the surface itself. It says here that the texture of a surface is going to affect how it reflects light. The manner at which light is reflected depends on the smoothness of the surface. Light that is reflected from a rough, not smooth texture surface, such as paper or cloth or just something that's not polished, is going to reflect in many different directions. So this is going to be a smooth mirror. And this is going to be a rough, not smooth mirror, right? You can see it. Look at the surface over here, nice and smooth. And then you can see this one over here is all jaggedy. What happens on this mirror, I can see that, man, this reflection is coming out and all of the light will reflect at the same angle. Oops. Is it angle EL? LE? LE. Whatever degree this is going to hit in, it's always going to reflect at the same degree. But look at this one over here. It's rough. It's not smooth. The light will reflect in different directions. It's going to be all different. You're going to look a little warped. You're not going to look nice and smooth in that mirror. Have you ever seen like those kid mirrors? You go to like Walmart or something, or if you have a younger sibling and they have those like little kid mirrors and you look at yourself, you know that's not how you truly look, but that's because the surface is not a nice smooth surface. It says here that this type of reflection is actually called, it has a name. Here is the vocab, diffuse reflection. Light reflected from a smooth surface, shiny, super smooth surface of that mirror, all of the light is going to reflect in one direction, oops, and not the band group, the same. Okay?
Is that how they make those mirrors that like fairs and stuff? You know what I'm talking about?
Right, like at a fun house, right? The fairs, a fun house. That's going to be the rough one. So you look at yourself and you're super long or you're kind of fat. Maybe you did gain a little weight, I'm not sure. But either way, you kind of looked a little warped. All right, so here we